Hi, welcome to lecture 10 of Hardware Software Co-Design for Edge AI. In this lecture, we'll be discussing about the design tools and methods for Zynq MPSoC and Kriya board. So before we start discussing the system design with Zynq MPSoC and do some practical labs in the lab sessions, it is useful to introduce the design tools, development boards, and the supported materials documentations that support this entire process. So in this video, I'll provide a main design flow which are available to us for designing with Zynq MPSoC. We introduce at a very high level about the different design tools and methodologies. So let's get started. So at the very highest level of abstraction, a Zynq MPSoC system consists of broadly the three elements, which is the board on which the Zynq MPSoC device sits, then the Zynq MPSoC hardware design which goes into the PL, and the software layers that run on the top of the hardware. And of course, this FPGA through this breakout board interacts with other peripherals via the interfaces which we have discussed. So in the lab sessions particularly, we will discuss the development boards which are commercially available from Xilinx. The typical prototyping board enables us to have a set of standard facilities and peripheral interfaces which you can see here. So once we have designed our IP, writing the code in either HLS or directly at the hardware description language level, on top of that hardware there is a stack of software elements which may include one or more operating systems along with the other application software and some, if you have RPU available, then with other real-time operating systems. So in the following slides, we'll discuss more about the hardware design and the software stack which goes in greater detail. But first we'll begin with an overview of the different elements that comprise a Zynq MPSoC system. One of the most standard boards which got released before even the Kriya board was this Zynq MPSoC ZCU104 board, which you can see right here on the screen as well. The name of the board is ZCU104 and the part number of the FPGA which goes inside this is ZCU7EV. So ZCU7EV, as we have discussed in the previous lectures, has 4 cores of ARM Cortex A53 processor, 2 cores of ARM Cortex R5 real-time processors, and an ultra-scale plus programmable logic having 504K logic cells and 1728 DSP slices. The Kriya board which we are using has lesser number of logic cells and the DSP slices. The rest of the things are quite similar. The memory has a QSPI flash, a 2GB DDR4 RAM which is attached to PS, and a DDR4 RAM memory socket attached to PL. So this is the in the board you can see that this is where the 2GB DDR4 memory sits for the PS side, and this is the memory socket for the PL side. The PL can also access this memory using a direct memory access, a DMA engine, as we had seen in lab 3 or lab 4 related to Pink board. Regarding the connectivity, we have Ethernet port, SATA M2 port, HDMI ports, display port, FMC expansion connector, USB 3, UART, micro SD card slot, and some PMOD ports which you can see are distributed all along the edges of this board. For programming the board, we can directly use a JTAG port which you can see here, or we can put it inside the QSPI flash memory, or we can use an SD card to boot up the system. Some other boards are also available from Xilinx and third-party vendors. From Xilinx, we have ZCU102 board, which is very similar to 104 board but has lesser number of resources. Two of the very famous boards are Avnet's Ultra 96 board. This board has a Wi-Fi module also along with it. It has some general purpose headers for it to connect with Raspberry Pi or Arduino. On the right, we have Xilinx or AMD Kriya KV260 board, and these are the connections / the interfaces which we can see from the development board. Note that the main Zynq, the main FPGA, sits inside this heat sink. Rest all of these are the breakout boards. So these development boards are a convenient starting point for most designs, but products are usually developed on custom boards. This enables a free choice from the full selection of Zynq MPSoC chips available, and also allows full customization for the target application, thus potentially achieving a physically smaller board that includes one of the components, only the components which are required with optimized cost and power consumption. So let's start the discussion with the hardware system. So when we are working with the Zynq MPSoC device, a number of hardware resources are available, which we've already discussed in the overview of Zynq MPSoC architecture, which primarily includes the PL, the PS and a selection of peripheral interfaces supporting various standards. In any particular application, it may not be necessary to use all the available hardware elements for a particular system, and designers have flexibility to include only the subset that meets their application requirements. The PL in particular provides a blank canvas, offering the freedom to implement any design. The designers create their own custom hardware using the Xilinx design platforms and sometimes also using the third-party design tools. The custom hardware includes the hardware resources particularly taken from the PS, any IP cores or other functionalities to be implemented into the PL. It takes some IO connections, it takes use of memory, the clocks and interrupt configurations and interfacing between all these elements. We will take a deeper example in the next slide, but just as a simple example, the hardware system may be designed to comprise the PS with Ethernet and USB interfaces and a custom IP core implemented in the PL. So this diagram is depicting the idea which we have just discussed. The complete hardware system represents the base upon which all the software elements of the system are built, and software runs on the PS and communicates with the hardware elements of the system. The hardware-software co-design process integrates both hardware and software components to optimize performance on these FPGA-based systems. The green, which is the PCB, refers to the development board, but inside that this yellow portion represents the PL and the blue portion represents the PS. Since someone of you is seeing it for the first time, I would highly recommend to go back to the overview of Zynq architecture to know what PL is, which is programmable logic, and PS, which stands for processing system. The hardware system PL can take inputs from the Vivado HLS, that is high level synthesis, and this tool is used to create custom hardware accelerators by converting the C++ code into hardware descriptions like VHDL Verilog. This allows developers to design, implement and validate their algorithms in high level language and then translate them into optimized hardware blocks for the PL. We have covered this Vivado HLS in one of the future recordings, which is lecture 12. Then the PL can directly use VHDL or Verilog, which are like the traditional hardware description languages used for designing custom logic, which is particularly useful when you have certain precise control over what hardware you want to deploy. Then we have a very interesting thing which is called IP integrator tool. So IP integrator library consists of IPs and other hardware components which are created by Xilinx, or can be created using the Vitis HLS and are integrated together using the IP integrator tool. It helps in connecting different IP blocks, defining the interfaces and managing the data flow between the different IPs in the programmable logic. When we come to the software side, the Vitis is used. Vitis is used to develop, debug and optimize the software running on the processing system, which can include application code, OS and other drivers. This software stack runs on the ARM processor within the Zynq MPSoC and allows communication with the hardware accelerators implemented in the PL. We have seen that in KV260 we have the option of running Ubuntu and Linux OS as well. The use of Linux provides a flexible and robust environment for running software applications on the PS. Linux supports various drivers and APIs that facilitate seamless interaction between the software running on the PS and custom hardware in the PL, and that is why the Ubuntu image running on your FPGA Kriya KV260, it might look very similar to any other Ubuntu running on your laptop, but it has the secret power of being able to interact with custom accelerators which you have deployed in your hardware. So let's look at an example and we'll see how together when these tools and methodologies work, they enable a very hardware software co-design approach where software and hardware components are developed concurrently. The ability to rapidly iterate between software and hardware modification is key to achieving the best performance and ensuring the system meets the design specifications. Let's now look at a complex block diagram illustrating the interconnection of various IP blocks within a Zynq UltraScale Plus MPSoC system. This diagram, this block design, represents a hardware design where the processing system PS and the programmable logic work together to perform data processing tasks using direct memory access, fast Fourier transform, and FIR filtering. The interconnections are made primarily through the AXI protocol, which is crucial for communication between different modules. Let's look at the key components, and the first one being the Zynq UltraScale Plus MPSoC block, which is the core of the system, which integrates the PS, including the ARM cores, and the programmable logic, which handles custom hardware acceleration. The PS interacts with the PL via several AXI ports. You can see here the S_AXI HP0 FPD port and the MAXI HPM0 LPD port. Let me quickly take you to the slide where we discussed about these interfaces. So you could see that we have the SAXI HP0 port and the MAXI HPM0 LPD port. Sorry, not this one, but the LPD port. So these two ports are used in this design to allow data transfer between the processor and the programmable hardware. Next thing which we look at is the AXI interconnect. This block manages the AXI bus interconnection between multiple masters and slave interfaces. It also acts as a communication hub directing traffic among the connected IP blocks. It handles several AXI ports which you can see mentioned here, and it facilitates high bandwidth data movement between the processing elements, the memory controllers, and the different IPs which are connected to it. One of the blocks which helps us manage the reset signals is the reset block. When executed, it sends out the reset signals for various parts of the systems, ensuring all components can be properly initialized or reset when needed. You can see signals like MB reset, bus struct reset, and interconnect asynchronous reset, which are crucial for maintaining system stability during startup or reconfiguration. Then let's move on to the AXI DMA blocks. So you can see two DMA blocks are there, AXI DMA and AXI DMA1, which handle high speed data transfers between the memory and the processing elements without CPU intervention, which significantly boosts the system efficiency. The DMA blocks are configured with the master and slave interfaces, which you can see right here, to handle memory to stream and stream to memory operations respectively. DMA is a very interesting block to understand and a very practical and a useful IP to be used for all the practical applications. So therefore, we might have a separate discussion on DMA if time permits. Next, let's come to the FIR compiler block. This block performs finite impulse response filtering, which is a common signal processing tasks used in applications like digital filtering, data smoothing, and signal analysis. The FIR block connects to the AXI stream interface using the S-AXI S data and M-AXI S data, which enables it to receive and process stream data efficiently. Now let's discuss the fast Fourier transform block, the XFFT block. The FFT block performs frequency domain transformation, which are essential in signal processing for analyzing signal frequency content. The FFT block is connected to AXI streaming interfaces, allowing it to receive input data and output processed data seamlessly. Next, let's take a look at the AXI4 stream subset converter, which converts AXI streaming signals between different formats, ensuring compatibility between different IPs and components with different AXI interfacing specifications. So it plays a key role in adjusting data paths between the DMA engines, the filters and transforms, and this is what we had looked in the resizer application as well, where we had created such a subset converter using HLS tool. Then lastly, one block is remaining, which is the peripheral block. So this block manages peripheral connections, ensuring proper signal routing and control across the system. It connects the various AXI interfaces, facilitating data flow between the PS and external or custom hardware components. So all in all, the functionality and flow of this diagram showcases a tightly coupled system where the processing system and programmable logic collaborate to execute complex data processing tasks. Data flows through the system primarily via the DMA engines, which feed the FIR and the FFT blocks, allowing rapid data manipulation without the CPU bottlenecks. The AXI interconnect and subset converters enable seamless data transfer across multiple paths, ensuring the system's flexibility and scalability. The purpose of this type of design is used in applications requiring high performance signal processing such as communications, radars, audio processing and more. But the main purpose of us is to highlight the capabilities of Zynq UltraScale plus MPSoC platform in leveraging both the hardware and software resources efficiently, providing a balanced approach to performance and programmability. Next, we'll discuss about the layered architecture for typical software stack used in embedded systems, specifically those involving hardware-software co-design such as Zynq MPSoC and Kriya platforms. So, hardware system, which is the bottom layer, is the foundation of the stack and consists of physical hardware components of the system. In the context of Zynq MPSoC, this layer includes the processing system and programmable logic and the peripheral hardware. It serves as the base that executes the instructions coming from the software layers above it. Note that why we have said programmable logic is because even in the PL we can have a soft IP by the name microblaze running as a processor inside that. Next comes the drivers and low level functions. This layer comprises device drivers and low level functions that directly interact with the hardware. Drivers act as intermediaries, allowing the operating system and the user application to communicate with the hardware without needing to understand the specific details of the underlying hardware architecture. Drivers manage hardware components like I/O ports, memory and other peripherals, providing a standardized interface to upper layers of the software stack. Low-level functions may include basic I/O operations like printf statements, interacting with USB or UART protocols, and some memory management routines and initialization of code necessary for proper hardware functionality. Next comes the operating system. So, this is the orange layer which you can see the operating system, which sits on top of the low level drivers and provides a higher level abstraction for managing hardware resources. In embedded systems, commonly used operating systems include the Linux or the FreeRTOS or custom real-time operating systems. We even have a variant of Linux called as the Peta Linux and even Ubuntu based systems running on FPGA. The OS manages the execution of user applications, handles scheduling of tasks, memory management, input-output operations and other system tasks. It also provides a standardized interface like system calls or APIs that user applications can use to perform tasks without directly managing hardware, which ensures stability and security. And at the top of the stack sits the user applications. These are software programs that perform the end user tasks such as data processing, control algorithms or graphical user interfaces. These applications rely on the OS for resource management and use system APIs to perform tasks like file handling, network communication or sensor data processing. In the context of a Zynq MPSoC, user applications may also include custom softwares that communicate with hardware accelerators in the PL using dedicated drivers and APIs provided by the OS. So, this complete diagram highlights that the layers are tightly integrated with each layer building upon the functionality provided by the one beneath it. There is a course called device drivers which is highly recommended for you to understand the drivers and low level functions which may exist separately or be bundled as part of the OS depending on the system's architecture. And this whole stack model ensures modularity, allowing each layer to be independently developed, tested and optimized. This layered approach simplifies the design, troubleshooting and upgrading of embedded systems by isolating changes to specific layers. So, most notably in the Zynq MPSoC, given that it has several processing cores split as APU and RPU, there could actually be several software stacks running. So, this is just one stack, there might be a separate stack running on a different processor or maybe a different core of the same processor. There may also be further software stacks in the system associated with the platform management unit, the video codec unit, the DPU, the deep learning processing unit, as well as any soft microblaze processor cores implemented in the PL. There are more permutations which are possible in Zynq MPSoC than the previous models Zynq 7000, which just has a dual core APU, because here in Zynq MPSoC we just don't have an APU, we have an RPU as well as a GPU, and the PL is obviously there. In a typical scenario where FPGA is deployed, we use both APU and RPU, And we will generally assume that two different types of operating systems are deployed. A desktop/embedded operating system like the Peter Linux or Ubuntu on the APU, and a real-time operating system like FreeTOS on the RPU. There are different possibilities which exist, ranging from using APU or RPU in isolation with a single OS, right through a more complex scenario where different operating systems are running on individual cores. Obviously, we cannot cover all the software stack possibilities, but we look at a more generalized or a more focused approach, which includes an adopted set which has a Linux as the primary operating system implemented on the A53 processors and a free RTOS deployed in the R5 cores in the RPU. Along with this, maybe some core can have a bare metal application running, which is just a standard application, a C code, without having any scheduling or memory management task. In terms of OS development, Xilinx provides the Peter Linux, which represents a set of Xilinx specific Linux development tools which can directly interact with the hardware. And there is also bare metal option, which is a lightweight operating system suitable for very simple tasks, available via the Vitis IDE. Because you might hear some of these terms as you read about FPGAs, so I will just introduce some third party options which include other Linux types like the Yocto project, which incorporates specific support for Xilinx Zynq FPGAs, and free RTOS for real-time processing. Further possibility includes Windows IoT and Windows embedded version, and something which is called as VxWorks. The Android operating system, commonly associated with all our smartphones and tablets, is another option, particularly for systems incorporating a touchscreen type user interface. So in summary, a Zynq MPSoC system can be considered to comprise a number of layers. Neglecting the PCB on which the Zynq MPSoC system resides, the lowest level is the hardware system developed by the designer, followed by the various layers of software from the low level drivers all the way up to the applications. Now let's discuss the design process for creating a Zynq MPSoC embedded system that can be categorized by a design flow, beginning with capturing the requirements for the system to be designed. So let's discuss a scenario where a designer or design team sit and consider the project in detail, making key decisions about the approach that will be taken and putting appropriate plans and schedules in place. In terms of actual design process, the flow refers to the sequence or stages or processes involved in creating the design, that is hardware and software components and the interfaces between them, and alternatives exist for the design flow. Surrounding issues include profiling, testing and documentation. So getting a requirement and specification is the most important task. When embarking on a Zynq MPSoC system design, a major initial task is to generate the set of functionality and performance requirements. This will capture the target features of the design, and ultimately it will influence all the design choices that follow. So the captured requirements can be developed into a formal specification of the system. With the end goals established, this will inform the selection of target device, estimates of the design efforts and the resources required, the composition of the design team, which might include the hardware, software, system engineers, algorithmic specialists, etc., the choice of design methods and development tools, as well as the general planning and scheduling. Undertaking a design based on the Zynq MPSoC is likely to be a complex project comprising a number of different elements and requiring the input of design team rather than just being completed by a single individual. The system may also involve commercial, security or other particular constraints that must be adhered to. Therefore, the scope in terms of planning and executing a Zynq MPSoC project is wide, and we choose to address this topic simply by posing a few pertinent questions that should be considered. First is partitioning, how will the system functionality be partitioned? In other words, which parts of the system will be implemented in hardware and which parts in software, and how will they be interfaced together? Then comes the hardware requirements. So what are the requirements for the target device? How large a PL is needed? How much on-chip memory does the application require? Are 2 APUs needed or 4, are 2 cores needed or 4 cores needed inside the APU? Are there any special features needed like the VCU in the PL? Then comes the software requirements. How should the software stack be composed? For each, which is the most appropriate choice for the operating system? That is for each core. Are there any requirements for hypervisors or other special components? Then comes the design tools / methods. What general design flow will be adopted? Which tools and methods will be used for developing the hardware and software components of the system? Definitely there has to be debugging and profiling. So will there be access for all engineers to a physical development board during the design process? Or would a virtual platform which is called KMU be useful? What strategies for profiling and testing and debugging will be adopted? Then comes the question of project scheduling and resourcing. What are the skills of the engineers who will work on the project? How long are the various design, interfacing and testing tasks likely to take, and what are the dependencies between these tasks? Clearly, there are a number of factors to bear in mind. So, it is worth studying the two design flow models which are outlined here in this diagram. First one, the standard method of design hardware and software separately approach, and the newer software defined approach based on the Vitis IDE tool. These are two alternatives and represents considerably different methods for designing for Zynq MPSoC. The traditional hardware software design flow and the more modern software design flow, both approaches aim to integrate hardware and software to achieve a specified functionality, but they differ significantly in how they handle the design process. So as we have already discussed, the design process begins with defining the system requirements and creating a specification that outlines the expected functionality, timings, performance and other constraints of the system. This initial stage is common in both the design flows and serves as the foundation for subsequent design decisions. So on the left side we have the hardware software design flow. So in the traditional approach, the design starts with the system design where software and hardware partitioning is done manually. This stage involves determining which parts of the system will be implemented in software and which in hardware, often based on performance, cost and design constraints. The series of lectures which will be taken by Dr. Vinay Chamola will help you understand these hardware software partitioning algorithms. Then comes the stage of hardware development and testing and software development and testing, and both of these are performed separately. Each domain works on its own component, developing and validating them independently before trying to integrate them into one full system. Integration and testing occurs after both hardware and software components are developed. The two are brought together and system level testing is conducted to ensure the components work seamlessly with each other. The flow involves iterative back and forth adjustments between the hardware and software, leading to a final system integration and testing stage where the complete system is validated against the initial requirements. This flow tends to be time consuming with clear distinctions between hardware and software development phases. It requires significant manual intervention to achieve hardware software co-design. Now on the right side is the more modern approach of software defined design flow. So the design starts with designing system functionality directly using software code. The initial emphasis is on creating a complete functional description of the system in high level language like C, C++ or Python. Then comes the functional testing, which is conducted early in the flow, allowing rapid iterations and adjustments to the design before hardware considerations are introduced. The iterative nature allows refining the design to match performance and functional requirements closely. After functional verification, hardware software partitioning is performed, where decisions are made on which parts of the code should be executed in hardware, the programmable logic, and which should remain in software. This partitioning can often be automated or semi-automated, relying on profiling data to guide the decision. The flow moves to evaluating the solution, assessing the system's performance and functionality with the current partitioning. So if the solution does not meet requirements, the process loops back further and for refinement between the hardware software partitioning. So the process concludes with the solution choice and final testing, where the chosen hardware software configuration is finalized and validated against the system specification. So this flow is characterized by flexibility and rapid prototyping, allowing more fluid transition between software and hardware domains. It reduces manual partitioning efforts and accelerates the overall development timeline. So the design tools available in the Vitis unified software platform include the Vitis IDE, the Vivado design suite, the Vitis HLS, Vitis AI and the Peter Linux tools. The Vitis IDE is a unified environment that allows developers to write, debug and optimize software applications, hardware kernels and AI models. provides a streamlined workflow for developing and testing applications using C++, OpenCL, Python. On the other hand, Vivado Design Suite is for use for designing, simulating and synthesizing the hardware portion of the application and supports high-level synthesis for converting C++ code into hardware blocks along with IP integration and the debugging capabilities. Vitis HLS allows developers to describe algorithms in high-level languages like C++ and convert them directly into hardware descriptions like VHDL or Verilog. Vitis AI provides optimized AI models and tools for deploying machine learning in applications on Xilinx hardware. It includes tools like Model Zoo, AI Optimizer, AI Compiler, Quantizer, which can compile deep learning models for efficient execution on the hardware. Then we have Peter Linux tools, which is used for designing custom Linux-based operating systems tailored for the Xilinx hardware. And it facilitates kernel customization, adding drivers, and building a complete boot image for embedded systems. So there are many development flows which are available in the AMD documentation. Few of the notable ones being the application acceleration development flow, the embedded software development flow, the hardware development flow, and the AI inference development flow. The application acceleration development flow, as the name suggests, focuses on creating accelerated applications using hardware kernels which offload the task from host CPU to programmable logic for performance improvement. The embedded software development flow is the one which we are going to choose in this course, and it is designed for developers specifically targeting embedded systems on the edge like Zynq MPSoC and CRIA-SOMs. It involves creating software that runs on the embedded processor, often interacting with custom accelerators implemented in the programmable logic. The hardware development flow, which involves interacting purely with Vivado and creating IPs written in hardware description languages, is suitable for bringing out very optimized designs, but this is not the flow which we are going to choose. So this diagram provides an overview of the Vitis Unified Software Platform, which is a comprehensive development environment designed to achieve and accelerate the development of applications. So at the top layer we see the domain specific development environments, which are tools which are commonly used for AI, video analytics, blockchains, allowing model based designs in MATLAB, and even networking components. Then one layer below we have the Vitis accelerated libraries layer, which consists of pre-optimized libraries that provide ready to use functions across various application domains, facilitating faster development by leveraging existing highly optimized code. So this include vision and image processing libraries for tasks such as filtering, enhancement and object detection, the math and linear algebra library supporting mathematical computations including matrix operations crucial for scientific computing and data analysis, the graph library for graph processing and analytics often used in data mining, network analysis, machine learning. Then we have high performance computing libraries optimized for computationally intensive tasks often found in scientific simulations and large scale data processing. Then comes the Vitis core development kit. So the core of the Vitis platform, this layer contains the primary tools and components used in the development flow. We here have the Vitis HLS, which we already know about, the RTL kernel wizard, which helps create and integrate RTL kernels into Vitis environment, and we have the AI engine compiler, which compiles AI models and code to run efficiently on AI engines within the AMD hardware. So the Vitis compiler and linker is a key component that compiles and links hardware and software elements into a single cohesive application. Then we have a Vitis analyzer tool to analyze the performance and help in debugging and visualizing the bottlenecks. Then we have the Xilinx runtime, popularly called as XRT, that provides a uniform API for communication between the host application running on the CPU and the programmable hardware. It handles all the data movement, kernel execution and system control. And finally we have the Vitis target platform, which can range from Zynq UltraScale MPSoC to Zynq 7000 Alveo cards, CRIA-SOMs, the newer Varium cards and the Versal cards. So some of you might be feeling that where do all the sensors go, how are they interfaced? So regular development boards include their own peripherals and usually one or more general purpose ports for adding expansion modules. So there are two main standard interface types called as PMOD and FMC, which give access to wide variety of peripheral functionality. So you can see these two interfaces in the board here, the PMOD ports mentioned here and the FMC connector written here. There are PMOD add-on cards, which are small and low cost expansion modules and include functionality ranging from simpler simple GPIO facilities to communication modules like Wi-Fi, Bluetooth, lower rate DACs and ADCs, and other sensors and actuators. PMOD literally stands for Peripheral Module. The PMOD is a proprietary interface type developed by Digilent. And many third-party vendors like the Maxim or the Analog Devices, they also support these PMOD ports. On the other hand, FMC expansion cards support faster rates like up to 40 GB per second and are typically used for higher value applications. This includes high rate ADCs and DACs, camera module, serial connectivity, SDR module for transmitting and receiving audio signal. Again, some of the vendors which make FMC chips are Analog Devices, Texas Instruments. So let's summarize what we have discussed in this video. We have introduced the various aspects of designing of Zynq MPSoC from a high level perspective. The composition of Zynq MPSoC and the roles of hardware and software components have been outlined with appropriate links made to the device architecture. We have covered the design flow alternatives and tools available for creating Zynq MPSoC designs. Some practical information was also included on hardware software co-designing, and we'll keep on discussing this later on. And lastly, we discussed the expansion cards and the modules which are available as third-party vendors. Thank you so much.